Hello everyone. Today in this live session we'll be seeing the contents of week 5 which is the subsurface water, and in subsurface water we'll be seeing some problems on infiltration. So these are the contents which will be covered in the today's session. So we'll be seeing some problems on double ring infiltrometer test and how to determine the potential and the actual infiltration rate, and as well as the cumulative infiltration depths, and we'll be seeing how to estimate the model parameters based on the given experimental data. So you'll be given some data with double ring infiltrometer test data, and you'll be asked to find out what are the parameters for different models like Horton's infiltration model or Phillips equation parameters, and the other models which are available. So we'll be seeing that problems, and for the final part we'll be seeing how to estimate the rainfall excess. In this you'll be provided with some infiltration model, and you'll be given some rainfall, and you should estimate what is the rainfall excess. So we'll move on to the first problem. So it is based on the double ring infiltrometer test. So the first problem is a double ring infiltrometer test is conducted on a soil with the porosity given as 0.4 and an initial moisture content of 0.1. So the area of the inner ring is 0.1 square meters. The total volume of the water poured during the experiment is 50 liters. Now we need to determine what is the depth of the wetting front. So how deep the water has infiltrated. So here we can also assume that all the water has infiltrated into the soil and it has a sharp wetting front. So we'll see how to solve this problem. So here they have conducted a double ring infiltrometer test. So let me draw the ground surface, and here we have the double ring infiltrometer which is hammered into the soil. So we have something like this, and let's say that this is the initial level of the water inside the double ring infiltrometer. So after some time the water starts infiltrating into the ground, and in double ring infiltrometer we have the vertically downward movement in the inner ring, and in the outer ring near the edges we have the laterally outward movement of water. So we use double ring infiltrometer test so that the assumption that we make while deriving most of the infiltration equation is that the water moves vertically downward. So we are not considering the lateral flow of water. So in the central region, so that is in this particular region, the water moves vertically downwards. And we also know that the soil moisture profile in the soil varies with the depth, and this axis represents the soil moisture content, which is theta, and the y-axis represents the soil depth. So we have different zones. The maximum amount of water which the maximum amount of moisture which the soil can hold is equal to your porosity, and the moisture profile varies something like this. So close to the surface, and here we have a depth of water which is available for infiltration. So close to the surface, we can consider the soil to be saturated after a sufficient amount of time, and later we have a transition zone. The moisture content starts to decrease slightly with respect to the depth, and we have the transmission zone. d theta by dz is almost uniform, and we have the wetting zone. Your moisture content with respect to the depth varies abruptly. And just below that you have your dry soil. So this is the soil moisture characteristic curve, and this is how it varies below the soil. So now in question we have been given assumption that we can assume the moisture profile to be a sharp wetting front, which means your soil moisture profile now can be assumed something like this. So this is your theta, and this is your z. So this is saturated, and here transmission happens, and this is your dry soil zone. Now we need to determine how much depth it has infiltrated into the soil. So basically we need to determine what is this edge. So for that we have been given with the data given depth of water, that is infiltrated into the soil is 50 liters. So we are going to convert it into the, this is the volume of water. Sorry. We have to convert it into the depth, and we are also given with the inner ring area. Area of inner ring is equal to 0.1 meter square. Now we need to find out depth of water that is infiltrated. So volume by area will give you the depth. So that I am coining it as HW. So 50 into 10 power minus 3 meter cube divided by 0.1 meter square, you will get 0.5 meters. So this is the depth of water that has infiltrated, but what is the length up to which it has traveled down? So for that we can make use of the porosity. So the definition of porosity: volume of voids to the ratio of volume of voids to the total volume. So if the soil is saturated, so your volume of voids will be equal to your volume of water. So I am going to make use of this condition. So porosity can be written as volume of water by the total volume. So I am going to multiply it with the area. I am going to convert it into area in terms of depth. So area of the soil cross section multiplied by your depth of water that is infiltrated. This will give you the volume of water divided by your area of the soil divided by the total length of the soil profile. So now we need to determine what is the capital H. So we can just rewrite this. So capital H is equal to HW divided by eta. So H is equal to 0.5 divided by, porosity is given as 0.4. So H is equal to 1.25 meter. This is below the ground level. So 50 liters of water has travelled around 1.25 meter into the soil stratum. That is what we have found. So moving on to the next question. So the second question is, a student performed a double ring soil infiltration experiment on initially dry soil until the infiltration rate approached a constant steady state value. From the data, the plot of natural log of excess from the constant steady state infiltration rate with time is given. And we have also been given with the data point. At time t is equal to 1 hour, the infiltration rate was 1.68 centimeters per hour, and the soil porosity is given as 0.45. Now we need to calculate the decay constant for the Horton's equation, the initial and the steady state constant infiltration rate, and we also need to show the variation of infiltration rate and the cumulative infiltration depth as a function of time. So we are going to plot both of this with respect to the time. And question number D, if the soil is initially wet, how will the infiltration rate curve change? And we need to provide a qualitative plot comparing the wet and the dry soil, and we also need to justify why is it happening like that. So this is the data that is, this is the plot that has been provided. So they have done some experiment and they have fitted a straight line, and this is given to determine the Horton's parameters, and they at t is equal to 1 hour, they have also given the ordinate value. So we'll be using this to determine the Horton's parameters. So we'll see the second question. So here we know the Horton's equation. Infiltration rate at any time t is equal to the constant infiltration rate plus initial infiltration rate minus the constant infiltration rate into e to the power of minus kt. So we are rearranging this equation. So f of t is f of t minus f of c is equal to f naught minus fc e to the power of minus kt. Taking natural logarithm, so we can now write this equation as ln of f of t minus f of c is equal to ln of f naught minus fc minus kt. So I can I'll rearrange it in another way. So this equation is of the straight line equation. It's in the linear form. Y is equal to mx plus c. Here your y is ln of f of t minus f of c. Your slope is minus k. Then x is t and your constant is ln of f naught minus fc. So these are all this is the components of the straight line equation. Now if you see the plot, this is a plot between your y as well as the x, and you have been provided with the equation y is equal to minus 0.22x plus 0.477. So I will write that equation. Given y is equal to minus 0.22 x plus 0.477. So the Horton's parameters. So the Horton's parameters are K, F naught and Fc. So these three are the Horton's parameters. So from this equation 1, we can estimate the value of K first. So K is nothing but the slope. K is equal to 0.22 and its unit is per hour. And we have been given at the time t is equal to 1 hour, your infiltration f of t is equal to, infiltration rate is equal to 1.68 centimeters per hour. So this data has been given to find your FC value. So if you see your capital, your y is given by ln of f of t minus f of c. And from the graph we also have y is equal to 0.257 at t is equal to 1 hour. So if we substitute all these values, your only unknown will be f of c. So we'll determine what is the f of c value now. So ln of 1.68 minus fc, which is the unknown, is equal to 0.257. So if we solve this, we will get 0.387 centimeters per hour. So this is your f of c. The last parameter is your intercept f naught, which can be obtained from the intercept. So your intercept c is given by ln of f naught minus fc. So in that in equation 1, you will get your intercept when x is equal to 0. When x is equal to 0, so we are going to substitute in the equation 1 x as 0. So if I do that, I will get y is equal to 0.477. So you will get y as 0.477, so which is nothing but your intercept c. So intercept c, ln of f naught minus fc is equal to 0.477. Now we found fc value, so we can determine f naught. So f naught minus 0.387, and if we solve this, we'll get f naught to be approximately 2 centimeters per hour. So the final parameters are 0.22 per hour, fc is equal to 0.387 centimeter per hour, and f naught is equal to 2 centimeter per hour. So these are the parameters. So now we can move on to the next part B of the question. So we have determined the part A and part B. Now we need to plot the variation of the infiltration rate and the cumulative infiltration depth as a function of time from 0 to 300 minutes at the interval of 30 minutes. So for that, now the Horton's model is So your infiltration rate, the potential infiltration rate, f at any time t is equal to fc plus f naught minus fc. This is 1.613 into e to the power of minus kt, and t is in hours. F is in centimeter per hour. And similarly, your cumulative infiltration depth. This is given by capital F of t, which is nothing but integral of 0 to t f of t dt. It is just the integral of the above equation. So your ft will be equal to fc into t plus f naught minus fc divided by k. So that is this is fc minus f naught minus fc divided by k into 1 minus e to the power of minus kt. So this is your expression for cumulative infiltration, potential cumulative infiltration depth. So now we need to take t as 30-minute interval and compute the potential infiltration rate and cumulative infiltration depth. Then we need to plot f of t versus time, small f of t, that is infiltration rate versus time, and cumulative infiltration depth versus time. So I have calculated and plotted. So this is how the plot looks like. So the red color line represents the potential infiltration rate, and the corresponding axis is on the left side. So you can see how the potential infiltration rate varies from 0 to 300 minutes, and the corresponding potential cumulative infiltration depth, for which the axis is on the right side. So this is how it varies. And so coming to the last part of the question, so it is given that if the soil is initially wet, how will this potential infiltration rate curve change? So this is the part D of the question. So if the soil is initially wet, the amount of water that is infiltrated, the rate at which the water infiltrates, will decrease. So The reason is, if the soil is wet, first what happens is so only the initial infiltration rate decreases, but the final equilibrium infiltration rate, that is your FC, remains unchanged. So it is the maximum rate at which the any particular soil can infiltrate. So that will not change. Only your FC changes. Now, if we see the infiltration rate graph, how it will vary is, so your x-axis is given by f of t, and this is with respect to time. So let's say if the dry soil initially has something like this, has the infiltration rate something like this. So this is your constant. This is when soil is dry. So now when the soil becomes wet, so your initial infiltration rate decreases, let's say here, but your final infiltration rate, that will remain the same. So this is let's say this is F01, and this one is F02, and this is for wet soil. So what other changes will be there? So sometimes the decay constant, which is the K, parameter K, may also change to fit the experimental data. So now coming to the reason for why F02 is less than F01. So we know that the vertically downward flow occurs due to the total head difference. And dry soils have a suction head which tends to pull the water. But in wet soils, reduced suction rate. So it also has some negative hit, but it is not as great as your as great when compared with your dry soil. Thereby, the total head difference in the dry soil will be more when compared with the wet soil. So this is the reason. So next we can see one more question. So your next question is based on the potential and the actual infiltration rate and the cumulative infiltration depths. So first we need to understand what is the difference between potential infiltration rate and the actual infiltration rate. So let's say that we have a rainfall that occurs with an intensity some intensity I with centimeter unit as centimeter per hour, and you have your potential infiltration rate. F in small f in centimeters per hour, and your potential cumulative infiltration depth. Capital F, that is in centimeters. So first is we will have two cases. Case 1, here we can say that if the rainfall intensity I is less than your potential infiltration rate. So which means the intensity of the rate at which the rainfall is coming down is less than the rate at which the soil can infiltrate the precipitation. So in that case, what will be the rate of infiltration? So the actual possible rate of infiltration is capital F, but the rainfall intensity is less. So the available water which can infiltrate into the soil comes at a lesser intensity than the rate at which the soil can infiltrate the water. So in this case, the infiltration rate will be F will be equal to your rainfall intensity. This is the actual infiltration rate. So in this case, we will be calculating the cumulative depth of infiltration as F is equal to I into the time step up to which your rainfall intensity is less than the potential infiltration rate. So this will be the actual cumulative infiltration depth. So case 2, if intensity is greater than F, so your amount of water that is available, that is coming, the rate of rainfall is greater than your rate of the potential infiltration. So in this case, F is the infiltration F will be equal to the potential infiltration rate. So this potential infiltration rate depends on the kind of model which we choose. It may be from your Horton's model, or it may be from your Phillips equation, or it may be from other empirical models which are available. So in this case, if it is Horton's model, your potential infiltration rate will be equal to Fc plus F0 minus Fc into e to the power of minus kT. So you will use this equation to determine the potential infiltration rate. So in this case, the actual cumulative infiltration will be equal to the potential cumulative infiltration depth. So here delta T is T2 minus T1. So here you will determine, based on the kind of model you have chosen, you will be using the equation to determine the cumulative infiltration depth. So in case of Horton's, it is Fc into T plus F0 minus Fc by K into 1 minus e to the power of minus Kt. So you use this equation to determine the potential cumulative infiltration depth. So now let's see a problem related to that. So here in this question, the potential infiltration rate and the rainfall intensity are given as some function. So your f of t varies as a cosine function, and the rainfall intensity varies as a function of sine. And here we need to plot the potential infiltration rate and the actual infiltration rate between 0 to 1 hour, and the potential cumulative and actual cumulative infiltration depth between 0 to 1 hour. So, and we can take the delta t as 5 minutes. So here first I have just calculated everything. So here the first column is the time, it is in 5-minute interval. Second column is the potential infiltration rate. So this has been determined based on the function which is given. So your capital F is calculated as per cos pi t plus 1 centimeters per hour. So that is your small f column, and adjacent to that intensity varies as a function of sine, and it is 1.5 sine pi t. So now we are going to check whether the rainfall intensity is less than your potential infiltration rate or not. So the fourth column is I greater than F. So for the first 5 rows, your rainfall intensity is less than your potential infiltration rate, which means the rate at which the infiltration is happening, your small f will be equal to I for the first 5 rows. So, and for that we need to find out the capital F as that is your cumulative infiltration depth as I into delta T, which we discussed just before. This is case 1. Your first 5 rows corresponds to case 1 and the remaining rows correspond to the case 2. So from the 6th row you can see that your rainfall intensity is greater than your potential infiltration rate. So the actual amount of infiltration that is happening will be happening at 1.289 centimeters per hour, and correspondingly we need to calculate the cumulative infiltration depth. And we are determining the actual infiltration depth also. So next we can see how the plot looks like. So the potential infiltration rate is marked in the red color, and your blue line is the rainfall intensity. So here up to the time t is equal to 20 minutes, the curve will follow the rainfall intensity pattern, and later it will follow the potential infiltration curve. So it will follow the pattern like this. So this is how your potential infiltration rate is varying. And this is how you see your rainfall intensity varying. So x is f comma I in centimeters per hour, and this is t in hour. So your actual infiltration rate will follow a pattern like this. So I'm going to draw that in green color. So this is up to t is equal to 20 minutes. And after that, it will follow your potential will follow this curve. So it will follow the green curve. So moving back to the presentation. So your potential cumulative infiltration has been calculated. So for the first 5 rows it will be I into delta T. For the rest of the rows it will be based on the integration of your small f of t. So this is how it varies. Now we can move on to the next question. Next question is based on the Horton's infiltration model. So the question is, during a storm event from 8 am to 8:30 am, the total precipitation of 2.5 centimeter was received. The infiltration rate in the basin during the storm were recorded and plotted as shown in the figure. So the infiltration potential infiltration rate and the time, how it varies with time, has been given to us. Now using the Horton's infiltration model, we need to determine what is the infiltration rate at 8:30 am and 9:30 am. And given that Horton's constant is 12 per hour, your K value is given as 12 per hour, and we need to determine what is the cumulative infiltration depth at 10th minute and cumulative infiltration depth between the 10th minute and the 20th minute. So we have been given the graph from graph. F versus T, we can determine the following parameters. So F naught is around 4.5 centimeters per hour and FC is 1.25 centimeters per hour, and your decay constant K is given in the question as 12 per hour. So now we can write the Horton's model for this. Horton's model is F at any time T is equal to Fc plus F naught minus Fc into e to the power of minus Kt. So we need to determine what is the infiltration rate at 8:30 am. So at 8:30 am, so time is equal to 30 minutes. So if we convert into hours, it is 0.5 hours. So small f is equal to Fc is 1.25 plus F naught minus Fc is 4.5 minus 1.25 into e to the power of minus k into t in hours. So small f will be equal to 1.258 centimeter per hour. Now at 9:30 am, time is equal to 1 hour. So your f will be equal to 1.25 plus 4.5 minus 1.25 e to the power of minus 12 into 1. So your f will be 1.25 centimeter per hour. So this is the first part of the question. Now coming to the next part, we need to determine what is the infiltration rate at the 10th minute. Cumulative infiltration depth at the 10th minute. So for that, we need to determine F at 10th minute. So F is equal to infiltration rate 4.5 minus 1.25 into e to the power of minus 12 into 10 by 60. So I'm converting the minutes into hours. So here F is around 1.68 centimeters per hour. Now we need to check whether it is always good to check whether F is less than I or not. So your infiltration rate is 1.68 centimeter per hour, and your rainfall has happened from 8 to 8:30 a.m. and total precipitation of 2.5 centimeter. So intensity is 2.5 centimeter per hour, and it happened for 30 minutes. So this is 5 centimeter per hour is the rainfall intensity. So your F is less than your I, so you can use directly. So now we can determine what is capital F. So this is given by Fc into T plus F0 minus Fc divided by K into e to the power of minus 1 minus e to the power of minus Kt. So all the values are found, we can just substitute directly. So if we do that, it is 0.443 centimeters at 10th minute. So this much amount of water has infiltrated. So now we can move on to the next question, which is related to your estimation of the model parameters based on the experimental data. So in this, we have been given a double ring infiltrometer test data. So the question is, in the double ring infiltrometer test, the water level for after every reading was reset to 100 mm by adding water. Before adding the water, the depth recorded is given below. So your time is given and depth of water after some time interval is given. So the amount of water that is remaining is noted down, and once it is noted down, they are filling the water again to the same level, which is 100 mm for every time interval. So now for this experimental data, we need to find what is the Horton's parameters, and we need to compute what is the total depth of water that is infiltrated until 100th minute, and total depth of water that is infiltrated from 15 minutes to 90 minutes. So these are the things which we need to determine. So we are given time in minutes. Depth of water in mm, and they are filling the water to the same level, and we need to determine what is the infiltration depth. Rate of infiltration. So the data is given in the question: 0, 5, 10, 15, 25, 45, 60, 75, 90, 110, 130, and depth that is recorded is also given. For initially it is 100, 83, 87. This is also given in the question. And after recording this, they are refilling the water to 100 mm. So this is the first time step. There is nothing. So every place they are refilling it to 100. Every time interval. So if we subtract these two, we will get the difference of this two will give you the depth of water that is infiltrated into the soil. So that will be 17, 13, 10, 15, 22, 15, 15, 15, 20, and again 20. Now we need to determine what is the rate. So that will be given by, so let's say if we call this as delta D, and this difference to be the delta T, so your infiltration rate will be delta D by delta T. So we can determine that. So it is calculated: 156, 120, 90, 60, and rest are 60. So now the experiment is done and we have calculated the rate of infiltration. Now we need to estimate the Horton's parameter. So one parameter from the table we can estimate directly. We have this constant infiltration rate. So this is nothing but your FC. So your equilibrium infiltration rate. So from table, your first parameter can be determined. So that is directly we can determine. Now what we need to do is, we need to take the Horton's infiltration equation, infiltration rate equation. So F at any time t is equal to Fc plus f naught minus fc into e to the power of minus kt, and we need to take the natural logarithm. So this is similar to the previously I have solved similar question. So it will become the it will take the form of this linear equation. So y is equal to mx plus c. So from the experiment, we have t and f of t. From table we found what is f of c. So with this information, what we need to do is we need to find out ln of f of t minus f of c for each time step. So we'll get the y-axis values and we have the x-axis. Next, what we need to do is we need to plot the graph. Plot ln of f of t minus fc versus time. So you will have some data points like this. What we need to do is we need to fit a straight line to this data point. So we will see how to fit. So something like this. We'll fit a straight line to this data point, and from this your slope gives you the k value and the intercept. Oops. Gives you the C value. So we'll determine this, and once you get that, you can determine what is f naught and what is the k value. So for that we will be using a method called as method of least square. So if you have access to Excel, you can just plot it directly and you can find out, but usually in examination you won't be allowed to use. So we'll see what is the method of least squares. So to fit a line, so we will determine what is the, we'll form a table. So what is x, what is y, and we'll find what is x square and what is x and y, x multiplied by y. So we need to form a table like this. and at the end of the table we will find what is the summation of x, summation of y, summation of x square, summation of xy. So once we determine that, we will frame two linear equations of the form. These are the two linear equations. So we will frame two equations like this. So here A is the slope parameter, B is the intercept parameter, so solving 1 and 2, find A and B. So here your A will be equal to K and B will be equal to ln of f naught minus fc. Then you can determine what is f naught. So this is how you will be determining the using the method of least squares to fit a line to the curve. So I have just tabulated that here. So here your table is given x, y, x square, y square and xy, and we need to find what is the summation. Summation is given in the, we need to find what is the summation and we need to frame this equation, and if we solve these two equations you will get your k and x. So and the equation, this is the equation you will be getting. Y is equal to minus 7.696x plus 5.175. So after fitting you will get an equation 7.696 x plus 5.175. So from this your k is equal to approximately 7.7 per hour, and your from the intercept ln of f naught minus fc is equal to 5.175. So if we solve that, we will get f naught as 236.97 mm per hour. So this is how you determine the parameters. Once we determine, we can write the Horton's infiltration model. F is equal to 60 plus 236.97 minus 60, that is 176.97 into e to the power of minus 7.70. So this is the Horton's model. Now we need to compute what is the depth of water that is infiltrated until the 100th minute. So your equation for capital F is Fc into T plus F naught minus Fc divided by K into 1 minus e to the power of minus 7.70. So this is your cumulative infiltration depth. So if we substitute T is equal to 100 minutes, we need to substitute in terms of hours. 76.97 divided by so if we calculate this, so this will be around 82.98 centimeters. So now we need to determine what is the depth of water from 15 minutes to 90 minutes. So here f is nothing but the integral between 0 to t, or let's say in this case t1 to t2 f of 2 dt. So what it gives is, it basically gives us the area under the infiltration rate curve. So if your Horton's infiltration is like this, so if this is T1 and this is T2, so by integrating, what we are doing is we are calculating this area. So this is what we want, but the equation gives, the equation for capital F gives area under the time which we are considering. So for estimating between two time periods, we need to find out what is the cumulative infiltration at T2, find out the cumulative infiltration at T1, subtract them both, or integrate the equation with the appropriate limits. So we can do either way. So what I'm going to do is I'm just going to find out your F is equal to at 90 minutes. So I'll term this as F90, answer into 90 by 60 plus 176.97 divided by 7.7 is 22.98 into 1 minus e to the power of minus 7.7 into 90 by 60. So I'll find out what is F90 first. So I guess here there is a mistake. So this is 112.98 mm, and this will be this is 122.98. So it's a small mistake, calculation mistake. So we have computed F90. So then we'll compute F15. At 15th minute, what is the cumulative infiltration depth? So your F15 will be equal to so this is 34.63 mm. So you require between 15th minute to 90th minute. So it will be 112.98 minus 34.63. So it is 78.35 mm. So this is the last part of the question. So the final question is how we will determine the rainfall excess. So after infiltration, there will be some portion of rainfall which will go as a runoff. We call that as a rainfall excess. So we'll see what is runoff once the runoff module starts. First we will see what is how to estimate the rainfall excess. And this question has been asked in engineering services mains examination 2013. So the rainfall over the basin in 3 consecutive hours is given as 4 cm, 5 cm and 3 cm. So each rainfall happened for 1 hour continuously, and we need to estimate what is the rainfall excess from the basin, assuming negligible surface retention and evaporation losses. The infiltration loss in the basin is modeled using the Horton's equation, and the equation for the potential infiltration rate is given. So F is equal to 1.2 plus 4.2 into e to the power of minus 2.5 t. Now we need to estimate what is the rainfall excess. So we'll see how to approach this question. So we have been given with the infiltration rate using the Horton's model. So it is in centimeter per hour and T is in hours. Now the rainfall which they give, I am going to draw the hydrograph of the rainfall. So first is 4 centimeters. This is for the first hour. Then for the second hour it is 5 centimeters. And for the third hour it is 3 centimeters. So this is at T is equal to 1, 2, 3, this is 0, and this is your rainfall intensity in centimeter per hour, as well as I'll be plotting your Horton's also, Horton's infiltration rate. Now we need to find out what is the initial infiltration rate, potential initial infiltration rate. So at time t is equal to 0, from the equation F is equal to 1.2 plus 4.2 e to the power of minus 2.5 into 0. So your F will be equal to 5.4 centimeters per hour. So this is your initial infiltration rate. So let us plot the initial infiltration rate. So this is so I am just writing the rainfall intensities. This is 3. So 5.4 will be somewhere, let's say here. So that is F naught. Now we need to find out at what time. So initial, if you see, the initial potential infiltration rate is higher than the rainfall intensity. Now we need to determine at what time step your rainfall intensity becomes equal to your potential infiltration rate. So now we need to determine at what time your F is equal to 4 centimeter per hour. So we can substitute in the equation. We have the Horton's model. Substitute F is equal to 4 centimeter per hour and find T1. So 4 is equal to 1.2 plus 4.2 e to the power of minus 2.5 T1. So from this we can estimate the T1, 0.162 hours. So from time t is equal to 0 to T1 is equal to 0.162 hours, your rainfall intensity is less than F. So actual infiltration rate F will be equal to I, and the cumulative infiltration will be equal to I into delta T. Right? So this is the only crucial point of this question. So if I draw the curve, now we need to determine the total infiltration depth, cumulative infiltration depth. I'm going to term this as capital I. This will be from infiltration that happened. Let me keep it as F itself. F is equal to F that happened from up to 0.162 hours plus 0.162 hours to 3 hours. So your F will be equal to your rainfall intensity multiplied by delta T plus this will be integration from 0.162 to 3 hours f of t dt. This is f of t dt. So f will be equal to your rainfall intensity is 4 and this is T2 is 0.162, T1 is 0 plus integration of 0.1622 So if we solve this, we will get a total infiltration of 5.174 centimeters. So this is the total depth of water that has infiltrated. Now to determine the rainfall excess, Q is equal to rainfall P minus infiltration. So your Q will be 12 minus 5.174. Q is equal to 6.83 centimeters. This is shaded in green. So if I go to the graph, whatever portion is shaded in green, that is your rainfall excess, and whatever is below that, your Horton's model, which I am shading in pink, that is the infiltrated water. So this is infiltrated and this is rainfall excess. So this is the water that is infiltrated. So in this we have seen different kinds of infiltration problems. These are very basic problems. In the next week we will be dealing with some more complicated problems. I am closing the session for today. Thank you.